everybody, and welcome to the NPTEL online certification course on microelectronics devices to circuits. This is the last module of this whole course. By this we will be finishing this module or this lecture series on microelectronics. The module name is memory design, and therefore we will be looking into the last section of the digital integrated circuits, and one of the application is usage of digital integrated circuits for memory. So, let me show you what is the outline of the course. The outline of the course is that we will be first introducing to you the memory itself, right, and then looking into memory classifications, a basic building blocks and its architecture, and then we will look at the memory core. Core means basically whenever you actually look into a memory, typically we have a core here. This core is the area where you are storing information, right, and you will have peripherals here, right. You will have peripherals here, you will have peripherals which will be responsible for extracting or writing the information within the core itself. So, the core will be actually storing the data, right, and the peripherals will be responsible for manipulating the data, which means that should be able to read or write the data. So, primarily read and write will be responsible for the peripherals. So, we will look into that, then we will look into ROM, read only memory, and non-volatile read write memory, and then read write memory as well, and then recapitulate the whole thing, right, and that is what the whole structure is all about. So, let us introduce memory here. So, more than half of today's transistor when we use in a microprocessor, the memory part of it are devoted to cache memories, and this is a ratio is expected to increase, which means that the cache memory is going to increase, and the reason is that the computational the computation is also increasing, and you need to store data for a larger amount of data, right. I will give you an example. For example, whenever you are discussing, for example, let us say an image processing algorithm, right, then you are actually taking an image and then breaking it down into pixels, and those pixels are getting processed at every stage. Now, so if your image is basically a high density image, the number of pixels will be very large, right, and therefore you require a memory to do that, and therefore it is very important that the performance of the memory is kept at the optimal level. What we try to do is that memory cells are combined into large arrays. So, that is an arrayed architecture, and why is it so? So that it minimizes the overhead caused by peripheral circuitry, which means that if I have one core and one peripheral, then it becomes very non-robust architecture, because then there will be if there are n number of memory cores storing n number of bits, you require n number of peripheral circuitry, right, and that makes life very difficult. Therefore, what people have done is that you have a core memory and the peripherals are therefore multiplexed across the whole memory, and this increases the storage density, as I discussed to you. The two important problems which are there in a semiconductor design is primarily, the first of all is the reliability, and the second is the power dissipation, right, and these are the two major concerns of memory designer, right. Reliability, when I say, I mean to say, are you able to reliably retrieve the value of the data from the memory code to the external port, or you are able to reliably write down the value of the external data onto the memory, right. What is your access time, what is your time taken to retrieve the data, and so on and so forth, right. Let me come to the memory classification, where memory classification we define that one core of memory will store maybe 1 bit of data, right. So, if you have a one memory core, we will see that later on, we will store 1 bit of data. Typically, chip designers express memory size in bytes. So, a group of 8 we represent them. We can also represent it in terms of multiple kilobytes, megabytes or gigabytes, right, the cache memory. Whereas the system designer will be storing in terms of words, how many words you are storing, which is the basic computational entity for the memory in a sense. So, these are the few areas in which but for our purposes, where as an electronic engineer or a designer, we generally refer to as bits. So, I will have 64 KB memory, I can have, or 256 memory KB, I can have a 512 KB memory, and so on and so forth, and therefore the array of the architecture which you require should be quite large in dimensions. Let us look at, and typically if you look at a array, it is typically a square array. So, if you want to generate a memory core, the memory core may be something like this big, and this should be as square as possible. The aspect ratio should be as close to 1 as possible, and the memory elements are all arranged in this fashion. That is the general trend which you follow, right. and this is the fashion which you go, and then you will have peripherals here, and you will have peripherals here, and you will have peripherals here. Then you will be recalling the data, and you will be writing the data. You will be recalling this data and this. So, by this peripheral you will be switching on this say cell, and by this you will be switching on this. So, by using these two lines I can select any particular cell and generate or write a data or read a data. Now, typically the time required, so there are certain timing parameters. The time required to retrieve from a memory cell is defined as read access time. What is read access time? See, so if already the data is there in the memory core, right, you send a read request, send a read request, and there is a certain time interval between the read request and the memory and the data coming to the output. That difference in time is referred to as a read access time, or we say RAT. So, if you see, these are the read signals which you see. So, the read signal goes high means you have sent a logic, or you have sent a signal to read the data from the memory core, and the data has been valid only at this particular point, or data has actually appeared in the output of this particular. So, in time domain this is basically my read access time, right. Now, the time elapsed similarly between write request and the final writing of the input data to the memory is defined as a write access time, and therefore, you see when I give a write access, this is my write going high, and the data is written at this particular point till this much point, then we define that to be as the write access time. So, this is the write cycle and this is the read cycle, right. So, the idea is to make the read and write cycle closer to each other, which means that the frequency of operation will increase, and you should be able to do that. But the problem is you cannot reduce the read and write cycle beyond a particular limit, and the reason being there will be always interconnect delays and so on and so forth, which restricts the high frequency operation of the memory. Based on, so timing we have understood, we have also understood basic timing we have understood, we have also understood the basic concept of the size of a memory. Let me explain to you based on memory functionality what are the issues available to us. So, a read only memory, and we have read write memory. Read write memory uses active circuitry to store data. So, it belongs to the class of volatile memory. Volatile memory is what? When you switch off the supply voltage, the data is lost, and we refer to that as a read write memory as such. Whereas ROM belongs to the category of non-volatile memory, which means that the disconnection of the supply voltage does not result in the loss of the stored data. So, whenever you, so all your, for example, whenever you switch on a computer or any of your devices, for example, even your mobile phones, tablets, laptops, the operating system, the OS is actually loaded on the ROM, right, because you do not want the ROM, you do not want the OS to be installed every time you switch on the system. It should be already pre-installed in ROM. So, even if you switch off the power when the power is gone, it is stored there. When you switch on the power, the OS gets activated from ROM, and you are able to do it. There are two types of other one, and this is EEPROM, electrical programmable ROM, and electrically erasable PROM, programmable read only ROM, and these are actually examples of non-volatile memory, right, and these are the few examples which is there for the memory. Now, how do you access the memory, right, and that is the most important part as far as timing and frequencies are concerned. Most of the memories which we will study is a random access memory, means which is basically that I can read or write any cell, right, in a random order. It is not that I have to, for example, the diagram which I drawn, suppose this is cell number 1, 2, 3, 4, 5, 6, 7, it is not that I will only able to read 1 and then 2, then 3, then 4, no, it is all random. So, I can even read 6 first, and then I come to 1, and then I come to 2, and then I come to number 4, and so on and so forth, right. So, this is the random access operation of the memory. However, there are certain memories which actually restricts the order of access, right. So, but then the gain which you get out of it is you get a faster access time and smaller area, right. For example, FIFO and LIFO are some of the examples. So, FIFO is first in first out, last in first out, LIFO is last in first out. So, if you look at read write memory, which is basically a your read write memory is basically your volatile memory. You have two, we have got SRAM, static random access memory, and DRAM, which is dynamic random access memory. In non-random access, so this is the random access, right, and then in the non-random access we have FIFO, LIFO, shift register, and CAM, right. So, content addressable memory. Right now you see for example shift register, you can have 4 types of shift register. You can have parallel in parallel out, PIPO, you can have first in first out, you can have first in last out, so on and so forth. So there are 4 types of shift register which are all giving you a random non-random access to you, whereas in non-volatile memory which is there we will have EEPROM, flash and EEPROM. Then read only memory we will have ROM and PROM. This is PROM, which is programmable read only memory, and these are all read only memory, and obviously as I discussed with you non-volatile memory. Let us look at a basic memory architecture which people have been doing it for quite a long time. And what people have done is that I can just show you here is that you store information in terms of bits, and these bits are stored in these words. So there are storage. So you see this marked here, your brown colored marked is basically a cell which stores 1 bit of information, and similarly for 8 bits of information we define this to be as 1 word here, and similarly you will have large number of words between this point to this point, right. So there are m bits, let us suppose there are m bits and there are n number of words. So there are n number of words. So there are n number of words with each word having m bit, and you can have therefore m into n is the total number of bits which you can store in this case, right. Now similarly, so what people do is that they put a decoder here in the input side, right. What does decoder do is that it's basically tries. So if there are say 8 number of select lines S0 to S7, right, say there are S0 to S7 select lines for choosing which word you want to read or write, then there are 8 lines which is available to me, then I require a 3:8 decoder. So there will be 3 address lines which will be inserting, and because with 3, so you see k is basically your log n to the base 2. So k is equals to log n to the base 2, right, well where n is the number of words which you see. So if the number of word is say 8, then you will have to, so number of word is 8, so log 8 you will get, and therefore you if you this, so k will be equals to log 8 by log 2, and this will be, so this you can break down into 2 to the power 3. So this will be 3 log 2 by log 2, and therefore log 2 will get cancelled out, k equals to 3. So I get k equals to 3 means you require 3 words here, 3 A0, A1 and A2 as the decoder input bits, right. So you require this into consideration. Similarly typically you require, so you have you can have row decoder as I discussed with you with values of A here, and you can also have column decoders which is shown here, and this column decoders will be attached with sense amplifiers. You do not have to worry what is this, but column decoders and row decoders allow you to choose a particular bit within the array structure of the memory core, right. So you have an array structure of memory core. So what I am trying to tell you is that I have an array structure of memory port, and let us suppose I want to choose this, then I will switch on this column, this row and this column. When I choose using the address decoder, I am able to choose this one, and now I can do reading or writing. So decoders helps you to choose a particular cell, and then I can read and write over the particular cell. Sense amplifiers or drivers are primarily responsible for making the circuitry fast, right, because you want to read a cell. So I will require that the voltage should come to the output side in a very fast manner, and that is required. It also allows you to give you a rail to rail swing. So VDD to 0 swing will be available through the sense amplifier design. This is the hierarchical memory architecture. If we go by step hierarchy, then we will see that we have an address row addresses, we will have column addresses, and therefore this row will have row decoders here, and therefore there will be block 0, block 1, block 2, block 3, so on and so forth, and these column addresses will be responsible for taking the column of the block, particular block. I will insert the block address here, and these will be responsible for talking with these blocks for extracting it. Then the global bus will be responsible for extracting the data or writing the data onto the system, which will be driven by this global driver or an amplifier, right. And of course there will be control circuitry, there will be a clock which will be driving it, and so on and so forth, which will be finally governed by the IO. So if you look very carefully to the whole hierarchical architecture, it is governed by a single IO, multiple IOs here, then you will have amplifier here, and then you will have a global data bus over which the data is being fed from external world into the memory or from the memory into the external world, and then you have got row addresses, column addresses and block addresses to ascertain from where the data has to be written or extracted. So, say you want to go for 7th block bit number word number 3 bit number 7, let us suppose, then these 3 information will be fed via block, column and row addresses, and then you can feed the data from the memory architecture. Let us look at the memory core. This is a read only memory, which is basically a volatile memory, a non-volatile memory, which I discussed with you. And therefore, for example, if the word line is high, this diode becomes switches on and 1 appears on the bit line, right, very straightforward and simple. Similarly, when word line high, this MOSFET switches on, this VDD appears here at a particular point. Of course, there will be one threshold voltage drop of the transistor, but that is immaterial at this stage. Similarly, so this is a diode based ROM. When you have a diode between bit line and word, so I have a bit line here, I have a word line here. Word line, so word line is done once like this for selecting the particular column, and the bit line therefore particular row, and the bit lines are responsible for selecting the particular column. Similarly, you will have MOS-ROM 1. So, this is the MOS-ROM 1, and this is again a MOS-ROM 2 where you have ground and bit lines, right, and so on and so forth. You can have various architectures for the memory core. Let us look at a 4x4 ROM array. In this ROM array, it is all MOS based ROM array, and therefore, let us suppose your WL1 is high, then what it does is that this BDD through this appears on bit line. So, your bit line equals to VDD. Similarly, if your WL2 is high, then I ensure that VDD is written onto bit line 1, right, bit line 1. Similarly, this will be written as so if this is WL2 is high, then I will ensure that this VD2 is written on this bit line, right. Similarly, if WL1 is also high and WL2 is also high, 2 word lines generally become high, then either if either of these 2 lines are high, then I will get a high on BL3, right. And there what I do therefore is I can therefore extract the information at particular cross section to the output world, right, and that is what we have been doing it in this case. Let us look at the non-volatile read write memory. Non-volatile is a switch off, your memory will be losing its data across it. One of the example is a floating gate, and then you have an EEPROM and you do have a flash EEPROM. I will request you to study all these if you are interested in this area, study a good book on memory as far as these read write memories are concerned. We do not have time to go into details of each memory architecture to give you an idea, but these are actually your non-volatile memory, right. So, when you switch it off, even so, for example, this floating gate, if you look at the floating gate, whenever you switch it off, the data is actually stored in this floating gate as a capacitance, right. So, if you ideally it will store the data for infinitely long duration of time, right, and that is the example of a non-volatile read write memory. Let us look at a static RAM, and one of the first example of a static RAM is basically your 6T cell or 6 transistor cell. So, if you look very carefully, this M5 and M6 are referred to as access transistors, right, access transistors, and this is basically a cross coupled inverter. So, if you just do one small job here, it looks something like this, right, it looks something like this. So, this is your word line, this is a word line, and this is your bit line and bit line bar. So, this is your bit line bar and this is your bit line. So, whenever my M5, so what is the, if I store 1 here, automatically 0 will be stored here, 0 will feed into this inverter and will make 1 here. So, this behaves as a latch, this behaves as a latch, which means that I am storing 1 bit of data here in this latch, right. Now, if I want to write or read a data, I just have to switch on my WL. When I switch on my WL equals to 1, then M5 and M6 switches on, right, and then this bit line and bit line bar or bit line and bit line bar gets access to the value of Q and Q bar here. So, if it is 1 here, you are 100% sure 0 will be here, this 0 will appear here and a 1 will appear here. So, if you want to read a cell, simply make, you have written a cell, suppose Q equals to 1 and Q bar equals to 0, simply make the word line high. Once you make the word line high, the access transistor switches on because it is an NMOS transistor. As it switches on, the value of voltages go on to bit and bit bar line, and you are able to therefore read the data from that particular cell. As I discussed with you, the read operation is something like this, that you have Q here, word line goes high, switches on this M6, and you are able to transfer this Q onto bit line bar with a 1 voltage threshold voltage drop. This appears across this patch, and therefore you have a VDD appearing here. Whereas, when you have bit line bar getting activated, this goes on, M5 goes on, right, since Q bar equals to 0. So, I have pull down getting activated, because VDD was attached to it, this is on, and therefore this goes to 0. When this goes to 0, 0 also appears as bit bar line and it is stored in the C bit here, fine. So, you have a C bit stored here, and that is the read operation. If I come to the write operation, what we try to do is that the same, exactly the same as the previous case. The only thing is that you are already bit line bar here 1 and bit line equals to 0. You again switch on WL because you want the access transistors to be on, and then you allow this 0 to be written through this arm. So, you had initially Q1 0 here. Now, if this goes to 0, right, if it goes to 0, this is switched on and this VDD appears here. So, here. So, you have to make your bit line voltage slightly higher to override this value, and therefore, this will be converting into a 0. So, this is the write operation for SRAM memory. Now, another example is basically my DRAM, which is dynamic RAM, and this consisting of also referred to as 1T 1C design, which is one transistor. So, this is one transistor and one capacitor, right, capacitor. And therefore, if you see very closely, when WWL is high, which you see this is high, this high means M1 is switched on. When M1 switches on, right, the bit line is suppose 1, the bit line is 1 and bit line 2. So, I have got bit line 1 is high at this stage and bit line 2 is remaining constant, let us suppose, and your RWL, which is the read line, has gone now high, right, is gone high here. So, when WWL is high, it switches on M1, and therefore, the value of voltage here starts to rise, right. Why does it starts to rise is that initially when this was, if your BL1 is high, and your M1 is switched on, this voltage will be written on this X and CS will get charged, and that is the reason you see an exponentially rising function at X, right, and that gives you a rising function. Now, let us suppose you want to read the cell. So, read this particular cell, then you make your read high. Once you make your read high, then you, and let us suppose the bit line has gone down, then you will see that at this particular point bit line 2, which is this one, right, bit line 2. So, when your read line goes high, this M3 switches on, you had stored data here 1, switch on, this will switch on your M2, and what will happen is this voltage will fall to 0, and therefore, you see that your bit line 2 is going down to 0, right, is going down to 0, and that way you can actually have the operation of a dynamic RAM. So, dynamic RAMs are therefore responsible for a 1T 1C cell. So, this capacitance CS is able to store the data till the next read or write cycle comes into picture, right. So, this is what the basic timing diagram of this is this. Let me recapitulate what we done for this memory design. You can actually look into, there are certain very important good books on memory, you can have a look into it. We can discuss it on discussion forum also regarding the books and open sources from where you can get this data. We have, what we discussed is that we have discussed the memory time, what is the meaning of various timing definitions, look at the access pattern and the application. We also looked into the fact that we have looked into the basic read write memory and volatile memory and ROM, which is basically a non-volatile memory. Finally, we went for RAM and we looked into a 60 cell, 6 transistor SRAM cell, and we looked also into 1T 1C DRAM cell, which is basically a volatile memory, an example of that, and how to read and write an information from a cell, right. So, these basic concepts I have made clear in this, tried to make you clear in this particular module. I hope you have enjoyed this module, and we look forward to meeting you during the NPTEL course structure when this is released. Thank you very much.